Today, we're going to learn about the conditional probability and the multiplication rule. So I'm going to do a little math today. All right, so our learning targets. I will know how to find the probability of an event given that another event has occurred. I will know how to distinguish between independent and dependent events. I will know how to use the multiplication rule to find the probability of two events occurring in sequence and to find the conditional probabilities. So, as we go along, write down the definitions. If you write things down, it gets better in your head. Otherwise, a copy of this slide presentation is available to you on Schoology as a PowerPoint. A copy of this presentation is also available to you on Schoology as a PDF for notes. After we learn this new material, we're going to start working on the classwork, and here we go. Conditional probability. The probability of an event occurring given that another event has already occurred. So you're going to see some jargon. It's denoted as P parentheses B vertical line A close parentheses, which is read the probability of B given that A. So that means the probability of a B event occurring given that the A event did occur. All right, so here's an example. We're going to find two cards are selected in sequence, one at a time, from a standard deck, 52 cards. Find the probability that the second card is a queen, given that the first card that was chosen was a king. All right, so we pick a king, and now we want to know what's the probability of finding a queen on the second draw. The assumption here is that the king that you drew on the first event was not replaced. All right, solution. Because the first king is taken away and not replaced, you no longer have a sample size of 52 cards. The remaining deck is now 51 cards. And because there are 4 queens, you now have a 4 in 51 chance of picking a queen, given that the first card was a king. So 4 out of 51, you make it into a decimal, it's approximately 7.8% chance. Here's another second example. The table shows the results of a study in which researchers examined a child's IQ in the presence of a specific gene in the child. Find the probability that a child has a high IQ, given that the child has the gene. So first, what was chosen, all the children looked at have the gene. Now we want to know, does the child have the probability of having high IQ? So first, gene present. So there are 72 kids that have the gene present. Now we want to look at, of those, which ones, what's the probability of picking one that has a high IQ? There's only 33 out of the 72 that have a high IQ. So the probability of having a high IQ, given that it comes from the subset of a gene present, is 33 out of 72, or approximately 4.58%. Independent events. The occurrence of one of the events does not affect the probability of the occurrence of other events. So it has no impact on each other. All right? So it's written as the probability of B, given A occurred, is just the probability of B. Or The probability of A occurring, given that B occurred, is just the probability of A occurring. So it doesn't depend on A and it doesn't depend on B. It's independent. Now, if the events are not independent, you can assume that they are dependent. All right, so here we go. Here's an example. Decide whether the event are dependent or independent. All right, selecting a king from a standard deck A, not replacing it, and then selecting a queen from the deck B. So the first event is picking a king. Then you don't return the card, and now you're going to, what is the chance of picking a queen? Because a king was first chosen, the sample size of 52 cards went down to 51. So the chance of picking a queen after king has been chosen is 4 out of 51. But if you started with a complete deck, the chance of picking queen without any other event happening first is 4 out of 52. So these are dependent. They're not independent events. All right. The second example, tossing a coin and getting a head is event A. Then rolling a die, a six-sided die, and obtaining a 6. So the probability of rolling a 6, given that you've first gotten a head on the coin, is 1 out of 6. The probability of just rolling a 6 with the die is 1 out of 6. Those two probabilities are equal, so rolling a die has nothing to do with flipping a coin. They're independent. The multiplication rule. The multiplication rule for the probability of A and B. The probability that two events A and B will occur in sequence, one happening right after the other. So the first is the probability of A and B. So the probability of A times the probability of B, given that A did occur. If they were independent, like the coin and the die, you would just multiply the two independent probabilities together. All right? And if there are more independent events, then you would just continually multiply them all in sequence. Probability A times probability of B times probability of C times probability of D, and so on, if they were all independent. All right, so here's an example. Two cards are selected without replacing the first card from a standard deck. Find the probability of selecting a king and then selecting a queen. All right, so what's the probability of selecting a king? It's 4 out of 52. And what's the probability of selecting a queen, given that you've already selected a king? And we've learned that was 4 out of a deck of 51 now, because you didn't replace the king. So you multiply these both together, and as you know, when multiplying fractions, it's numerator times numerator and denominator times denominator. So 4 times 4 is 16. 52 times 51 is obviously 2,652, which I'm looking at the answer. I could not do that in my head, which is 0.6% chance of occurring. That's why you do not win at cards very often. Here's another example. A coin is tossed and a die is rolled. Find the probability of getting a heads and then rolling a 6. These two events are independent. So the probability of getting ahead is 1/2. The probability of rolling a 6 is 1/6. You multiply them together and you get 1/12, which is 8.3%. Now here's another example, and we're going to do some complements, all right, which can be a little confusing, so we got to pay attention. The probability that a particular knee surgery is successful is 0.85. Find the probability that 3 knee surgeries are successful, 3 in a row. So that would be 0.85 times 0.85 times 0.85, which is 0.614. Now, probability does not always correlate to real life. One would hope if a knee surgeon performed 5 surgeries in a row, the probability of having all 5 of them be successful would be much higher than the statistical analysis of multiplying 0.85 together 5 times. So the probability of all 3 surgeries being successful is 0.614. Let's find the probability of none of the 3 knee surgeries being successful. All right, so what's the probability of 1 knee being unsuccessful? Well, it would be 1 minus 0.85, which would be 0.15. So all 3 of them sequentially being unsuccessful would be 0.15 times 0.15 times 0.15. All right. So there's only a 0.3% chance that none of the 3 were successful, because we found the complement of it being successful and then multiplied them together. Now, let's find the probability of at least one of the 3 knee surgeries being successful. So what's the probability of none of them being? Is 0.00, let's go back, 3. Then the complement would be at least 1. Could be 1, could be 2, or it could be all 3. So it's going to be 1 minus 0.003. So the probability of at least 1 is successful means the complement of them all being unsuccessful. So that's 1 minus 0.003. So we have a 99.7% chance that at least one of them will be successful. Hope none of you getting knee operations soon. So here's another example. Let me first say that in this section, as you see, there's a lot of reading. You're going to have to go weed through the reading, maybe with a pen or a highlighter, and pick out the important numbers. Those are the numbers you're going to use to calculate your probabilities. All right, so more than 1,500 U.S. medical school seniors applied to residency programs in 2009. Of these, 93 were matched to a residency position. 82% of the seniors matched to a residency position were matched to one of their top 2 positions. Medical students electronically ranked the resident programs in their order of preference, and the program directors across the United States do the same. The term match refers to the process where a student's preference list and a program director's preference list overlap, resulting in the placement of a student for a residency position. All right, so let's break this down. More than 1,500 U.S. medical students, 2009. Do those 2 numbers matter to us? No, they do not. All right, 93%, which is 0.93, were matched to a residency. All right, so what does that mean? Matched to it. 0.93 got a job. All right, 0.93 got a job. 82%, which is 0.82, got a job that they wanted. All right, they were matched to one of their two top positions. So 0.93 got a job, and of those, 0.82 got a job that they wanted. All right, so with that information, with those numbers highlighted, let's answer the question. Find the probability of a randomly selected senior was matched to a residency position, and it was one of the two top ones. So the probability that he got a job and the probability that it was a job that he wanted. So A is matched to a job. B is one of his top two choices. So probability of A is 0.93. Probability of getting the two top choices, given that he got a job, is 0.82. So the probability of A and B is the product of these two percentages. Because these were dependent. You can't get one of your two top positions if you never got a job. You have to get a job first, and then of that job, it turns out to be one of your two top positions. So these were dependent events. All right. Second example. Find the probability that a randomly selected senior that was matched to a residency position did not get matched with one of the senior's top two positions. All right, so probability of getting a job, and then probability of not getting one of his top two positions. So this is, you use a complement. So probability of not getting what he wants, but he did get a job. So it's going to be 1 minus the 0.82, which is 0.18, or 18% chance that he didn't get a job that he wanted, but he did get a job. All right, so in summary, we found the probability in an event given that another event occurred. And the key point in this is the sample size was changed. Like in the cards, the first event probability affected the second probability. We also distinguish between independent and dependent. And we use the multiplication rule to find the probability of two events occurring in sequence and to find the conditional probabilities